Hello class and welcome back. This is ME 354 lab number 4. Today we're going to be measuring the fracture toughness of 3 different materials while they're loaded under tension in the presence of a crack. We'll be following ASTM standard E399 for the specimen configurations and test procedures. We'll go over that as well as the load frame. We'll be using a different load frame this time. The fixturing, the data acquisition, the data we're going to collect, as well as some observations we're going to make about the fracture surfaces after the test. So let's start with the specimens. So these are our 3 materials. We have 2 plastics and a metal. On the left here we have acrylic. In the center we have polycarbonate. On the right we have 3D printed titanium alloy. So here's the schematic of the compact tension specimen as specified in ASTM E399. If you notice, most of these dimensions scale according to the W dimension, this dimension here. That dimension is measured from the center line of the loading holes to the back of the specimen. Our B dimension here is recommended to be W over 2. But we can vary that. In our case, it's going to be closer to W over 4. For the plastics, it'll depend on the as-received thickness. And for the printed specimen, we wanted to save material, so we printed those to be 6 millimeters. The A dimension is a dimension that we're going to measure and record in this lab, and that's our crack length. The A dimension is measured, again, from the center line of the holes to the leading edge of the crack. So one of the things we need to measure during this test is the crack opening and how it changes. So in order to do that, we've added these features to our specimens, a little pocket with these knife edges. That will allow us to mount this clip gauge, which is similar to the extensometers we used in the tensile tests. There's 2 cantilever arms here. If I squeeze those together and clip it on, it'll just stay there using spring force. So once we start the test, the clip gauge will move with the specimen and we'll get a readout in our data acquisition system in millimeters. Let's take a look at this load frame here. This is the Instron 8511. It's a servo hydraulic machine, which means there's a hydraulic pump that drives this actuator up and down with a range of plus or minus 50 millimeters. We have our load cell down below here. And then we have our adapters here and our compact tension fixtures. So our specimens will slide in, we'll pass a pin through to grab the specimens, and that'll allow us to apply our load during the test. We have a clip gauge here that's going to allow us to monitor and record the opening of the crack. Over here is the control panel where we program in our waveforms to control the actuator. We're going to be using a cyclic waveform for the pre-crack of the titanium specimen. And for the rest of the test, we'll use a ramping waveform to fracture the specimens. For the plastic specimens, we'll be using a ramp rate of 10 newtons per second. And for the titanium specimens, we'll be using a ramp rate of 80 newtons per second. Then over here, we have our data acquisition system, which will allow us to monitor and record the sensor inputs. So part of the specimen preparation is to create a pre-crack. So for the plastic specimens, you can see that we've already done that. You can see these pre-cracks here at the root of the notch. The notch is machined in where we remove material. The pre-crack needs to be made in such a way that no material is removed, and we just have a clean crack separating the upper and lower part of the specimen. For these specimens, all we did was take a razor blade and tap it into the root of that notch there until we have about 1 millimeters of pre-crack. To create a pre-crack in the titanium specimen, we have to use the load frame. It's loaded into the machine to a mean load and then cycled above and below that mean load at about 10 cycles per second for as long as it takes to grow a crack from the root of the notch about 1 millimeter out. Now I'm going to load up the titanium specimen so we can get our pre-crack going. It's going to take a little time, so we want to get that started. I'll first turn on the pump, a little loud. I'll take the specimen and get it lined up at the bottom. Put my pin in, lower it down, get the other pinhole lined up. Okay, jog it up a little bit until my pins are snug. It feels good. And now the last thing I'll do is install this clip gauge. So that is the configuration. We have our clip gauge installed, specimen ready to go. I'll get the data acquisition set up and we'll start pre-cycling. So we've begun our fatigue pre-cracking. Here's a close-up of the notch area. You can see our vertical line there, the silver line. And you can see that we're cycling at 10 hertz, 10 cycles per second. So we'll keep this up until we get a crack that develops all the way to that vertical line. So I've stopped the cyclic fatigue pre-cracking. It's difficult to see now, but we do have a pre-crack. I'm going to jog up just a tiny bit, and you can start to see that crack separate at the root. Okay, we've got our acrylic specimen loaded into the grips. You can see our clip gauge arms here mounted to the specimen. We've got our starter notch, and at the end of the starter notch we have a small pre-crack, a couple millimeters long, and there's a vertical line marking the end of that pre-crack. Up in the upper left corner we have the workspace from our data acquisition system, and we're going to be plotting load on the y-axis in newtons and displacement on the x-axis in millimeters as measured from the clip gauge. All right, let's go ahead and get this test started. And here we go. You can see our plot developing, linear to this point. You can see our crack is slowly extending past our mark. There goes our crack and failure. Now we've got the polycarbonate specimen loaded up. I'm going to go ahead and start the test. Okay, we've got our titanium specimen loaded up. You can see you can't see the pre-crack here, but it extends from the starter notch all the way to this vertical line here. Let's go ahead and get this running. There's a close-up of the acrylic specimen after fracture. We have the leading edge of our starter notch here, then a smooth, shiny surface up to this first red line. That's our pre-cracked surface. and then a slightly more striated shiny surface between these two red marks. That's our crack propagation region. And then after this crack propagation region, we have our fracture surface. So the final A dimension, the crack length, will be measured from the center line of this loading hole to the leading edge of the crack prior to fracture. And here's the polycarbonate specimen. You can see the same features here. Our starter notch edge, our pre-crack region, smooth shiny surface, and then a crack propagation region with got a few more striations, and then our fracture surface here. And finally, here's the titanium specimen after fracture. It's a little less obvious where the regions transition, but here's our starter crack edge. This is where our pre-crack ended. There's a slight change in color. It's hard to pick up on the film here. We have a crack propagation region all through here, and then after that, this rougher surface is after fracture. And here are the three specimens lined up together. Here's the 3D printed titanium, here's the acrylic, and the polycarbonate.
That's all for Lab 4. You'll receive 3 data sets for each material for a total of 9 sets of data. Thank you for watching and see you next week.